Hi everyone, welcome to day 2 of the Aerospike User Summit. Thank you for joining us today. In this session, we're going to talk about probabilistic data structures, the sorts of problems that can take advantage of this, and how we can use probabilistic data structures in Aerospike. I'm happy to see many familiar names. I want to say faces, but I can't this year. But happy to see many familiar names joining us today. But for those of you who don't know me, my name is Chang. I'm a solutions architect here at Aerospike. In my previous life, I was a software engineer at Google and a series of startups before that. I do come from a background in computer science and math, so be warned, there's a little bit of math coming up. With me today, we have Kevin Porter, who is the software engineer at Aerospike, who brings you this feature, so you have him to thank. So let's look at some of the common problems faced in the big data world. We want to count number of unique users in that visit a site. Or if we have a set of these user data, how do we aggregate them to get a total count of unique users over a larger period of time? Or we want to identify demographics for better targeting ad campaign. Retailers will want to look at user extensive purchase histories to more effectively recommend products to their customers. And perhaps a more relevant example today is, suppose we've got sequenced the genome of a known pathogen. How do we compare that to a database of known pathogens to find potential antigens and in our efforts to develop a new vaccine? So these sorts of problems generally involve either finding the cardinality of a data set, that is, determining how many unique items there are in the set, finding the unions of data sets, or finding the intersections of data sets. So let's look at the first question. So a popular website, according to the internet, that may or may not be named after a rainforest in South America, received over 2 billion hits in a month earlier this year. How many unique visitors were there? Well, very simple question, right? Simple answer. We can just sort the user IDs. Sure, that works, but not very efficient. So what else can we do? Well, improve the runtime, we can use a hash. Okay, that's better, but it still takes a lot of space. But we can improve upon that. So I'm going to talk about the HyperLogLog data structure. It doesn't yield a precise answer, but it produces an answer that's good enough. And this is an example of a probabilistic data structure. So we're going to talk about data structures first before we dive into probabilistic ones. What are they? Well, they are a way for us to capture, organize, and retrieve information. I'm sure you're familiar with many data structures, and just think about your favorite one and think about adding a piece of data to this data structure. There's probably a way where you can retrieve that exact piece of data back out from the data structure, but that doesn't always have to be the case. So think about the JPEG image. It is an example of a data structure that takes as input a bunch of pixel data, organizes them, and allows you to retrieve pixel data back out of the data structure. But the pixels that you retrieve out are not necessarily identical to the ones that you put in. In this case, the data structure has been optimized to reduce the amount of storage space required to store this image, and the ones that you put in. Pardon me? I just heard someone speak up. Okay, Sorry, I think there's some echo on the line here. So in a JPEG image, you can store pixel data. It organizes it a little bit, and you can retrieve pixel data back out to produce an approximate image that visually is fairly indistinguishable from the one that you put in, but at a reduced data size. We think of this JPEGs as a lossy image compression, but it really is a data structure that stores our pixel data for us. So probabilistic data structures operate similarly on other sorts of data. The ones we're going to talk about are statistical models that are efficient to compute, and they approximate the calculations on the data set that we care about. Let's go back to our example of counting unique users. We have a large data set of user IDs, and we're interested in finding out how many unique ones there are. I'm going to describe one way where we can do this. Let's take a random hash algorithm and apply that to each of these user IDs. We're going to get a collection of random hash values. These values are, because by nature of our random hash algorithm, these bits are going to be very random. So I'm going to, for my convenience, put this collection over here on the page. And let's look at the binary representation of each of these values. Consider the first bit. If it's a 1, let's put it in one side, and if it's 0, let's put it on the other. And we'll create two buckets. So we now have two buckets, one bucket containing all the hash values whose first binary digit is 1, and one bucket whose first binary digit is 0. Let's repeat this process with the second digit. We'll then end up splitting our data into 4 buckets. Now, if we keep repeating this until there's only one hash value in each bucket, and say we've done this k times, then we have 2 to the k buckets with one single hash value in each one, and 2 to the k is now an approximation for how many different unique elements we had in our original data set. So if you look at the bottom hash value here, you'll see that all of the k digits that were used to select it are 0. And so we can use the number of leading zeros to very quickly calculate k since k is then the maximum number of leading zeros in all of our hash values. But hang on a second, I hear you say. The data set is not always going to be a power of 2. In fact, it unlikely is going to be a power of 2 in size. And in any random distribution, you're not going to get all of your hash values at the same depth in this tree. And so it's not going to be accurate at all. And you're very right. So HyperLogLog allows us to specify as input a number of index bits. It allocates these bits out of each hash value and uses them to subdivide your data set into a number of subsets that it runs the HyperLogLog algorithm through each one of these to produce a k value. These k values are then combined together to give a much more accurate estimate. The more index bits you allocate to HyperLogLog, the more accurate the estimate will end up being. There is a cost of a little bit more memory, but it's still a lot more efficient than any of the other algorithms. And in the case of, say, in our examples, we're going to use 12 index bits. That uses about 3K of memory to store all of this information. So now we can consider some code. But before we get into how we would code this up in Aerospike, let's look at the operate function in the Aerospike client API. I'm sure many of you are familiar with this function, but for those who aren't, this is a very powerful function in the client API. It allows us to perform many operations on one record in the database in one single transaction. And if the transaction is the right transaction, the record is written once after all of the operations have been executed. So in my example here, I'm going to be showing how this is done in Java, but this operation can be done in all of the client APIs. So how do we do this? First, we create an Aerospike client connecting to the host and the port. And next, we define the list of operations that we want to perform to a record here. So in this example, we're going to write the string value1 to bin 1. We're going to write the integer value 20 to bin 2. We're going to retrieve the contents of bin 3. We're going to append the string hello to the list found in list bin. And we're going to look in the bin map bin and find the value corresponding to the map key and increment it by an amount increment. So these are the operations that we want to perform to a record. Well, we choose the record by using the key, and then we simply call the operate command on the client. This returns a record with our results, and we can get the value that we retrieve out of bin 3 from this record that has been returned to us. So that's the operate command for those who haven't seen it. And I highly recommend that you check it out. It's very, very useful function. It's very efficient as well. If you have to do a number of operations on a single record, it saves a lot of network, and it will perform much faster than in executing the operations individually. So now we can look at how we can use the operate and use HyperLogLog in Aerospike. So let's start with a data set. In my example here, I'm just going to be very lazy about it. I'm creating a data set that fits entirely in memory. But the HyperLogLog algorithm data structure doesn't really require that. You can add your data elements all at once. You can add them in batches, or you can add them, one at a time, however suits your application. But suit my needs of being lazy, I'm going to add them all at once. And also for simplicity of the code to be shown here, I'm going to do it all at once. So I'm going to create a smallish data set that fits in memory. And so I have actually used a hash set implementation, the standard Java hash set, to do the calculation. And we can see that there are roughly 100,000 unique elements in this set. I measured the memory. Java is not very good with memory, but I tried by forcing a garbage collection, waiting a little while for it to complete, measure the size of the heap, run through our hash algorithm, and then check the size of the heap again. And I got that we consumed about 21 megs of memory in doing this calculation. So it's okay, but it's not great given that this is a fairly small data set. So let's look at how we do this with HyperLogLog. First thing we want to do is we want to create a HyperLogLog data structure to hold this information. So we start by creating a list of operations. We use the HyperLogLog operation init to create a HyperLogLog object. and we initialize it with 12 index bits. So as I mentioned earlier, the more index bits you choose, the more accurate this algorithm will be at the cost of a bit more memory. In this case, with 12 index bits, we're going to use about 3K of memory, and we'll get about a 1.6% error, which for our case, we think that's good enough. So that's what we'll choose. You can use index bits in the range from, you can use up to 16 index bits in HyperLogLog here. So after we've initialized our HyperLogLog bin, we will create an operation that adds the data from our data set A into this bin. We create a key for the record that we want to operate on, and we apply the operations to this record. Now we have a populated HyperLogLog record containing information. We want to retrieve that. One operation that we can do on the HyperLogLog record is Getcount. GetCount returns the number of unique items estimated for that data set. So if we apply this to our key referring to the record, we get that the count is just under 100,000, which matches very closely to what we calculated out of the hash set. And as you can see, the size of the HyperLogLog data structure is 3,083 bytes. All right, so that answers, or that provides a good answer for cardinality of a set. Next, we're going to talk about how to get the cardinality of a union of two sets. So we have our HyperLogLog value representing the set of the data set A. Let's retrieve the HyperLogLog record from there. So it's just a get record out of the database. In this case, it's a client get to get the bin, and to retrieve the actual HyperLogLog value, we use the record.getHyperLogLog value function. Now, just to prepare ourselves for the next step, we're going to put this into a list. So we'll create a list containing a single value that's the HyperLogLog data representing data set A. So now let's consider a data set B that we want to perform our union with. We create data set B very similar to how we created data set A, right? We, again, another in-memory data set, and we create we use the init operation on the HyperLogLog data structure. Again, we're specifying 12 index bits. Ignore min-hash bits for now. We'll talk about that later on. And then we add the data from dataset B into this bin. We apply it to a key record, or for the record, and we apply the operation to this record, and we can then use the getUnionCount operation to retrieve information out of this record. So what the getUnionCount operation does is it takes a bin. In this case, we're going to use the bin containing the HyperLogLog representing dataset B, and we pass in a list of HyperLogLog values. In this case, we're passing in a list containing just one single value, the HyperLogLog data that represents dataset A. What this will return is the estimated count of the union of the bin that we have, dataset B, and the list that we're passing in, dataset A. And you can see the bottom line there, using HyperLogLog, 12 bits of HyperLogLog, we estimate the count to be 149,000 unique elements. Again, running the same, manually merging sets A and B and running hash sets, we see that there are exactly 149,998 unique elements. So the answer is fairly close. And in most big data applications, this sort of margin of error is acceptable. And in fact, in a lot of big data applications, your data set is changing while you're doing your operation. So you're never going to get an exact answer anyway. All right, so I'm going to skip ahead of some math that if we had more time, I was going to talk about, but I'm going a little bit slower than, I put them in case I had more time, but I don't think I will. So we're going to talk about how we do intersections with Aerospike. To do intersections, we can take advantage of a HyperLogLog data structure as well, although there's another algorithm that's used. It's called the Minhash Algorithm, and it's just a very standard algorithm that is known for basically sampling different data sets, subsampling different data sets in a way that's statistically meaningful. But there's a variation of the Minhash algorithm called the hyperminhash, where instead of storing the hash values as integers, we store them as an exponent, where we use the number of leading zeros of the hash value as the exponent and the remainder as a mantissa. And so if you recall, the number of leading zeros we've already calculated for HyperLogLog. So this is why we built the hyperminhash on top of the HyperLogLog, because we're reusing some of the same calculations that we've already done before. And so we're able to much more efficiently use this hyperminhash algorithm to calculate an intersection without having to redo a whole bunch of different calculations. So let's look at how we could do this in Aerospike. So the important thing here is that we want to allocate some number of minhash bits. We can use 0 minhash bits, but it's not going to be as accurate. Again, the more minhash bits that we allocate, the more accurate it's going to be. So the setup is very much the same as how we had set up the union example. I'm going to go back to the union slides. I'm going to reuse the union slides, except that in this case, we're going to set minhash bits to 4. So we have our data set represent for data set A, and we create a HyperLogLog, initialize a HyperLogLog data structure with some number of minhash bits, in this case 4, and we add the data for data set A into this bin. We get a record and apply the operation to the key representing our record. We then can read the value out of that bin, get the HyperLogLog value out of there, and we add that to a list. Next, we have our data set B, where again, we initialize a HyperLogLog bin with our 4 minhash bits, and we add the contents of data set B to this bin. We get a key for the record that we want, and we apply operate to this key with the HyperLogLog operations. So now we have a HyperLogLog record B that contains that captures the data we have in data set B, and we have a HyperLogLog list that contains a HyperLogLog value capturing the data in data set A. Now we can use the HyperLogLog operation get similarity to retrieve the similarity between sets B and A. We get a key for the record that we want. We apply the operation to this key, and then we can get the record back out. And we can see that there is a similarity of about 33%. There's also a get intersection count operation that we can use to get the exact count. In this case, the intersection is going to be just under 50,000 elements, which makes sense if we have two data sets of 100,000 elements with an overlap of about 50,000 of them. The intersection is going to be about a third of the union, and that corresponds to our similarity here. So using the HyperLogLog and Minhash algorithm data structures, we're able to address many of these big data problems. The first question here is just a cardinality count, HyperLogLog. Second question is the cardinality of a union of sets, HyperLogLog. The third, fourth, and fifth are all intersection problems. They can all be reduced to intersection problems. And so in this case, we use the HyperLogLog with the Minhash bits. So I think that's quite a lot to have covered in one day. So I'm going to stop now for questions. See if anyone has anything that they want to ask. Right. I see from the questions here. Ebron asked, is there some kind of table that shows the percentage error by the number of index bits? There is, in fact, on our HyperLogLog documentation, there is a table that shows how many bits corresponding to the percentage error. It's actually calculatable, and it's inverse proportional to the square root of the number of index bits is the formula, but there is a table in our documentation that shows exactly the percentage error for the number of index bits. Okay, and then let's see, which languages are supported for HyperLogLog? Currently, HyperLogLog is supported in Java, C#, C, and the REST API. We have Go, Node.js, and Python coming very soon, like within a month or so. So yeah, those ones are coming up soon. See what else. Do we need a separate table for this data type? This data type is it's just a standard data type that you would put in a bin. So just in your Aerospike, you just create a new bin that is a HyperLogLog data type, and that's all you need to do. Okay, just to clarify, union operation is not lossy while intersection is lossy. With probabilistic data structures, in a sense, it's all lossy in that you're not producing a precise answer. The union operation is the same as just a straight, you can conceptually think of it as the same as just a straight cardinality operation, right? In the cardinality example, we're estimating the number of unique elements. We're not going through them and counting them uniquely. So the answer is going to be an approximation and within the bounds of the error. Okay, Alexis asked, compare memory usage, but what about processing time? That's a very good question. With HyperLogLog, to ingest the data, you still have to look at every element in your data set, right? So you're still order n in processing, in inputting the data into the data structure. What you can do with HyperLogLog, and this actually ties into another question about how, what benefits are there for reworking an existing application. I'm going to cheat and tie these two together. Sometimes you're capturing, reams and reams of data just so you can do one analysis on there, on that data set, or a handful of analysis that you do after the fact. But suppose you have your data set of user IDs, and the only thing you actually care about in that data set is the number of unique users there are. In this case, you don't actually need to store all of these user IDs if you use the HyperLogLog. As the user ID comes in, you add it to the HyperLogLog data structure, and you can discard the source user ID information because we've already captured that information in our data structure. So we can add data as it comes in. It's still going to be order n time with Alex's question, but we're saving a ton of storage of keeping these individual data records that we otherwise wouldn't need. We can get the unique count estimate out of the HyperLogLog data structure without ever having to refer to these elements again. So there is a second processing time involved with retrieving the estimate out of the data structure, and that correlates to the number of index bits that we choose, because the number of index bits that we choose determines the number of k values that we produce. And in fact, the number of different subsets of the HyperLogLog we have is 2 to the power of the number of index bits. So if you increase the index bits by 1, you're doubling the number of HyperLogLog registers that you're maintaining, right? But even with 12 index bits, that's 2 to the 12, which is 4,000 registers. To compute the estimated cardinality, we have to look at then 2 to the 12 different values and compute a single harmonic mean out of these 4,000 values. But on the grand scheme of things, computing one harmonic mean from 4,000 values is actually not a whole lot of time. So that's fairly negligible as well. So processing time, aside from your ingest of order n, is going to be very, very fast. So yes, I should have mentioned earlier, HyperLogLog runs very, very fast. And it's much faster than even using a hash set, where you still have to, after the fact, look at the size of your hash. All right, go back to the question list. So, is using the min hash bits always better if you can spare the space? Well, it doesn't really take a whole lot more space on the grand scheme of things. In the example I had given earlier, if you're, if you want to do some statistics on your unique users, if using the min hash bits allows you to do your computations, right? If your analysis of the users is limited to intersections and unions, and you don't need to look at the individual user IDs that the piece of data that go into the data structure, then yes, using min hash bits is always better because you're not having to keep all of this extra data around. You add it to your data structure, you capture as much information out of that as you can within the HyperLogLog data structure storage, and you can discard your source data. So yes, if you can spare the space, I would say that using min hash bits is always better. All right. Go back to the question list and so internally, is this min hash implementation taking the k lowest hash or taking the min of k hash? Kevin, that would be a perfect question for you. Oh, Kevin has followed up to say that the min hash implementation follows the algorithm described in the hyper min hash paper. So, do you know, Kevin, if that is taking the k lowest hash or the min of k hash?
So you could kind of think of it as for each kind of bucket of when you count the number of zeros in the HyperLogLog for each register, we keep the minimum hash for that register. When the number of zeros in that bucket that we're counting increases, then we start collecting a new minimum hash for that register. Actually, the implementation maximizes it for performance reasons, but the paper describes it as minimizing and then mentions that you can maximize instead for performance reasons.
Okay, thanks, Kevin. Okay, I have another question here. Someone's put in an answer, but I'll read it out loud anyway. If the HyperLogLog is a namespace that is in the namespace that stores on disk, does it store everything on disk or take extra memory? The HyperLogLog data structure is just like any other data structure in Aerospike. If you have your namespace configured to store on disk, the data is going to be stored on disk, and the memory is just going to be the index for the record to find that record on the disk. And then let's see what other questions has not been answered. Jack wants a link to the paper for hypermin hash. Yes, we will provide that at the end. We can send that out to everybody who attended this. Right. Kevin, I'm sorry. I've been talking and not paying as much attention to the questions. Which questions have I not answered? It's just a bit of a list here, so I'm trying to go through them. I think I've covered all the questions. I will go through the remaining questions offline, and if there's any that's been missed, I will be sure to answer them, and we'll collect all of the questions and have answers for them and make them available as well. So thank you everybody for attending. I hope you enjoyed the rest of the summit, and I hope this session was useful and that you learned something today. Thank you.